Hello, everybody, and welcome to this week's edition of Dome to Home. Now, this week we'll be talking about the sun and other stars out in the galaxy and the universe, but we're going to go ahead and wait a couple minutes, just make sure that everybody gets on in here. Make sure you refreshing their screens. Just a reminder that a lot of the visuals that we'll be taking a look at will be most easily viewed or best viewed in full screen mode. So we'll go ahead and feel free to say hello in the chat. Hi, Elijah. See, we got a couple returning people, Zion, Samuel, Ronan. Hi, Ronan.
Yeah, and as people are coming in, if you want to take a look at the picture of the Orion Nebula and see what you notice there, it's lots of really interesting things to find.
See who else. We got the floor gang, whoever the floor gang is. Apparently they're in there. Mike is here. Dylan's here. Hi, everybody. Alexander's hi here. Avery's here. Hello, Avery. Hi, Aaron. All right, just a couple more minutes here. Let's see who else we got in here. Benjamin's here, Renzo's here, Josh is here, Eli's here, Boonstar's back. Margaret, hello. Alexander, Joseph, lots of people in here. All right. So it's been a couple minutes. I think probably good to kick things off here. Once again, welcome to the Dome to Home series. This is week 5, I believe, of this series that we've been doing. Bring in all the visuals that we can show you guys in the Fiske Planetarium in Boulder, Colorado, right into your homes, on your screens, laptops, and maybe mobile devices or whatever. My name is Jeremy. I'm a navigator and presenter at Fiske Planetarium. Down below, we've got Parker. Parker, how are you doing today?
I'm good. How are you doing, Jeremy?
Oh, doing swell. It's a great day.
Yes, it is. I am also a navigator here at Fiske Planetarium, bringing the dome to your home as well.
All right. Also joining us kind of behind the scenes, we have Rainey and Amanda. They're going to be working, moderating that chat and making sure we can kind of sift through all the questions and make sure that we're trying to get to everybody's questions. We've got a lot of stuff we want to talk to you guys about and not a whole lot of time. So hopefully we're able to get to all your questions. If not, you can always shoot us an email with in the links in the description. Or also comment on the actual video and not in the chat. So let's go ahead and get started. As Parker said, what you're seeing on screen now is a nice, beautiful image taken of the Orion Nebula, located in the Orion constellation. And this is a star-forming region. We're going to be talking about kind of the life cycle of stars, how they're born, how they die, and kind of how our sun fits into that. And so we'll get to this nebula here a little bit later in our show, but just real quick, I would like to point out kind of how kind of the finer filaments of this nebula are working. You can see kind of areas where maybe new stars are popping into existence and being created. Looks like maybe Parker, is there a way you can maybe angle up your camera a little bit, make sure we're centered all in here? And when Parker's doing that, he will also be able to lift us off of Earth, and we'll go ahead and drop into orbit of the Earth and take a look at our home. Here we are in a nice, safe orbit of Earth. I think that's the South Pole looking, we're looking down on the South Pole right there. Yeah, there we go. And so, like I said, this is going to be a show about stars. Our nearest star, of course, being the sun, our home star, providing all that green, awesome material known as plants and life here for us. Now, when you look up at the sun, there we go, we see it coming up in the sky here. A lot of times, obviously, the sun looks kind of stagnant or maybe a little bit calm in the sky. I do want to note that you shouldn't be staring at the sun unless you have a pair of, specially made observing glasses. It's not good to stare at the sun. It can definitely damage your eyes. Do not recommend to do that. Oh, there we go. Even looks like Parker's got some sunglasses. I don't know how much those will protect you, but if you could look at the sun with a solar telescope or something like that, a lot of times it looks kind of calm, maybe like a constant star in our sky. But in reality, the sun is a very violent and active object in space. While we're here on the Earth, I want to talk about a little bit of how the Earth interacts with the sun, or how the sun impacts things on Earth. A lot of you guys have probably heard of things called solar flares or coronal mass ejections. And what we're going to, let's go ahead and take a look at kind of what those are and why they have an impact on Earth. So if we think of this tennis ball right here as the sun, obviously this is not the greatest demo, but we got to make do with what we have in these times, right? So we have the sun rotating on its axis. Now the sun is not a solid object. Like I said, it's a ball of hot ionized gas, meaning that it can go through this thing called differential rotation. So basically, regions on the equator of the sun actually orbit faster than regions at the poles. And so the sun has these things called magnetic field lines that are generated because of all that churning hot gas and ionized gas. And so if we imagine that maybe this rubber band, make sure I'm centered here, this rubber band is maybe one of those magnetic field lines. As that sun is spinning, those magnetic field lines still spin with or rotate with the sun a little bit. But over time, due to that differential rotation, these magnetic field lines can get, a little bit kind of tangled up and things like that. And so just like spinning a rubber band, maybe that as I spin this more and more and more pressure and kind of tension is built up in that area right there. And eventually, the rubber band or the magnetic field line, in the sun's case, won't be able to, hold any of that pressure, and it will kind of snap back and maybe explode. And what's Parker is showing for us on the dome right here is a nice image, or movie rather, taken of the sun. So located at the very center, we have the sun, and you can see some of those flares and CMEs shooting out from the sun. Let's go ahead, and looks like Brooklyn wants to know what element makes up most of the sun. That is a great question. We'll take a look into kind of what elements a lot of stars are made of. Short answer for you, Brooklyn, is that the sun is mainly made up of hydrogen. It's going through this thing called nuclear fusion, which is the process of basically making new elements, and we'll dig into that a little bit here in a couple of minutes. So let's get back to these solar flares. We see these massive energetic events getting shot out from the sun, highly charged particles, deadly, really dangerous radiation. And luckily, Earth, being a very large, massive object, and it has an active kind of core, or a active iron metallish core, it generates its own magnetic field. And so Parker can bring up the magnetic field lines of our own Earth. And this magnetic field helps us to defend ourselves a little bit from these massive solar storms. There we go. These blue lines showing the orientation. Obviously, you can't see these lines in space. They are invisible, but they are there. And so what happens is when these solar particles are leaving the sun, come hurtling towards Earth, they get intertwined in these magnetic field lines and accelerated down towards the Earth. And this is the process that creates one of the most beautiful and kind of mesmerizing situations or scenarios on the Earth. And of course, I'm talking about the aurora borealis in the northern hemisphere, and the aurora australis, I believe, in the southern hemisphere. Phenomena, that's the word I was thinking of. Beautiful phenomenon. So solar storms can create, beautiful phenomena, great for, viewing, and, a lot of cool science can come from that. But some of these solar storms, if they're big enough, some of the solar particles can actually kind of get through those magnetic field lines. And that can be bad news for a lot of things on Earth and a lot of things in space as well. So I think Parker's flying us over to one of our neighborhood orbiters, the International Space Station. Yeah, here we are coming up on it now. And so you can think that if the sun is expelling these, large quantities of, radiation and solar particles, it's not a good time to maybe be floating around out there in space. If you get hit with these particles, you think of like you get a sunburn when you're down here on Earth. If you're up there in space and you get hit with a giant solar flare, it's not going to be a good day for you. And so that's why a lot of science and a lot of research is trying to go into studying the sun to understand how the sun is going to be acting, how it's acted in the past, and how we can make predictions on how it will act in the future to protect things like satellites, the ISS, obviously, and astronauts up there in space. Let's see here. We can see if maybe Parker can zoom back a little bit and maybe bring up some of the satellites that we have. Some solar storms, if they're big enough, they can knock out full power grids or knock out satellites. And in our ever changing and ever increasingly technological age, or technological world rather, we are becoming more reliable on these satellites. So for example, these are the orbits of all of our GPS satellites. So the solar storm is coming down and hits one of these satellites and knocks it out. We not only do we rely on it, a lot of these satellites in our everyday lives, trying to get to the store, back, or whatnot, but we also rely on these kind of from a defense standpoint and like a military standpoint. So there's a lot of research kind of going on in this area. And so let's go ahead. This is kind of the impact that we see from the sun here on Earth. Let's go ahead and have Parker fly us to the sun so we can get kind of an up close and personal view of the sun. And when he's flying us over there, let's go ahead and pop into the chat, see if we got some questions here. Let's see here. Looks like Aaron would like to know how big a common satellite is. That's a great question, Aaron. It depends on, I guess, what the satellite is made for. There's, can be things called CubeSats that are, kind of have, I guess, a limited scope of what they're trying to accomplish. And so in that case, we can make them, pretty small because they only have to do a couple things and they can do them very effectively. So in that case, they can be maybe the size of like a tissue box. In some cases, like maybe like telescopes and things like that, like the Hubble Space Telescope, they can be up to the size of maybe like a school bus. The issue is that it costs a lot of money to put things into space. So it's very valuable to be able to make things small and efficient to save costs on basically getting those satellites up into space. Looks like, oh yeah, just for some reference on what I said CubeSats are, they're usually about like 2 pounds, maybe like 4 inches by 4 inches. So very tiny little guy. Looks like we're getting pretty close to the sun. Here we are. So this is maybe the view of the sun that a lot of you are kind of familiar with. The sun is a yellow dwarf star, and we basically call it that because it kind of looks yellowish in our sky, when in reality, the sun is kind of emitting at white light, so basically all visible wavelengths. And we'll be taking a closer look on kind of the classification of stars and how our sun fits into that. Before we dive into that, let's go ahead and let's take a look at the surface of the sun. Yeah, there we go. So Parker's brought up a nice little model of our surface of the sun. And so this is the region of the sun called the chromosphere. So basically the transition between kind of the inner regions of the sun and the sun's atmosphere. And let's go ahead and bring up a even better image. So the sun is definitely an area that a lot of research needs to be done, but it's tough to do. Obviously, the sun, like I said, puts out all that radiation and things like that, so it's tough to get really close. Scientists have just recently kind of sent the Parker Solar Probe to the sun, which is going to be it's orbiting at the closest. Yeah, Parker is giving a little woo. It's the closest thing orbiting the sun in terms of science, or even planets, things like that. So that is kind of some space-based telescopes that we've sent out there that can take a look at the sun. What Parker has just put up here is the highest resolution image that we have ever taken from the sun. Now, this didn't come from the Parker Solar Probe. This actually came from a telescope on the Hawaiian island of Maui called the D-KIST telescope. It is a telescope that, or at least for this image, it took it in about 789 nanometers. So just to give you guys a reference, it's a little bit outside the visible spectrum on the redder side of the spectrum. And what you can see here is the really fine details of that sun's surface. What you're seeing are these solar granules, this little like these yellowish kind of popcorn kernel-y looking things. Each of those is about the size of like Texas. So these are huge, like kind of granules, and this is where we get that we see the convection process happening, transporting heat from the interior of that chromosphere up to the surface. And so those like brighter yellowish regions, those are the centers of the granules where the heat is rising, just like if anybody's ever boiled water to make tea or oatmeal or mac and cheese, you know that water boils like because of convection. So heat rises in the center, and then as it rises, it cools, and then it drops to the sides and comes back down. So these yellow regions are where that heat is rising up. Those dark kind of patches around encircling all these regions are where that heat is rising or lowering back down and kind of cooling off. Now, in between, in some of those dark little regions, you can probably see some of these really bright, almost white-looking areas. And those are actually little pockets of really strong magnetic fields that are forming on the surface of the sun. So this is kind of one view of the sun, the highest quality or the highest resolution image that we've ever been able to take of the sun. Let's go ahead and take this image down, and let's take another view of the sun. Let's go ahead and like take a slice out of the sun so we can see kind of the interior, how things are working, and some of the boundary regions. Because I've been throwing a lot of kind of jargon at you, like the chromosphere and convection and all of these different terms. Let's go ahead and zoom in here. So here we see that bright red region in the center of the sun. That's the stellar core. This is basically the region where we're having nuclear fusion. Oh, we lost the sun. There we go. That's where the stellar core is fusing hydrogen into helium and creating new elements. And as I said, we'll get to the more kind of intricacies of nuclear fusion shortly when we start talking about different types of stars. But then moving out from the core, we have this radiative zone. So photons, which are particles of light, or light particles, they're generated in that core, and then they start to radiate outwards in the sun until they reach that next boundary, which is essentially when the convection can occur for bringing up energy in those kind of like in those solar granules. Let's go ahead, and it looks like we got a couple different questions coming in here. Do countries coordinate orbits of satellites so they don't crash? Yes, absolutely. I wish, unfortunately, on this kind of viewport for you, it's really hard to kind of see satellites in our system because of how small they are, obviously. But the Earth is enshrouded in satellites, and 100% different countries must work together to make sure that those satellites don't crash. What stage of star life cycle is our sun in? Yeah, so that is the main sequence cycle. We'll be kind of discussing that here in a little bit. And can we walk on the sun? No, so it is basically what we call a plasma. So it's just a ball of hot ionized gas held together by gravity. So unfortunately, you can't walk. If you had like a really, I mean, it'd be very hot, so you probably couldn't withstand it. But yeah, you cannot walk on the surface of the sun. So let's go ahead and take a look at how big the sun actually is. So here we have a different model of what our sun looks like. These little dark patches are what we call sunspots, basically highly magnetic areas of the sun. Sometimes some of those can even be like about the size of the Earth. Let's go ahead and rotate around. Yeah, so Parker's showing us to scale what some of our planets would look like compared to our sun. So the sun is big compared to our own Earth. If our Earth was the size of a nickel and you put it up about, like next to your doorway, that whole doorway would be the actual size of the sun. But let's go ahead and talk about some of the other stars. This is not just a show about our sun, but about stars in the universe and the galaxy. So our sun is really big compared to us, kind of because we're very close to it, but also because, in actuality, the size of the sun seems pretty big. But when we look at other stars in the universe, we see that our sun is actually not nearly as big as some of the other stars. Let's go ahead and bring up a model of Rigel and Betelgeuse, Parker. So Rigel and Betelgeuse being stars in the constellation of Orion. Many of you might be familiar in it. Here we see that bright blue star popping up and the bright red star. The blue star is Rigel, that red star is Betelgeuse. And so when we look at different stars, looking at color is a big clue and can tell astronomers something about those stars. Now, if we could bring up the picture of a candle flame, and we can talk about why color shows you temperature. So blue colors in nature, unlike your faucets at home, blue color is actually a hotter color. It contains more energy than a redder color. So when we look out at the nighttime sky and we see different colors of stars, we can infer something about that star without actually going there. We can know that a blue star has more energy, it's hotter than a red star. And being cognizant of time, let's go ahead and Parker, can you start bringing up some of the different size comparisons of stars that we have?
Loading right now.
Want to make sure that we get to the stellar life cycle for you guys.
So I'm going to bring up the orbits here for a little bit of context on size. And then we have our sun there in the middle after I get rid of Rigel in the background. So I'll orbit around. The first star I'm going to show is named R136A1. It is a blue giant star. So we have that, all that right there compared to the sun. You can kind of see the size difference. The next one I'm going to show is Rigel. So there we have Rigel, which is part of Orion. Next we will have the Pistol Star, which is a lot larger. Another blue giant star. And then after that, we are going to show what we showed earlier, which is Betelgeuse compared to the sun. A lot larger. This is a red giant star, much larger than our star will ever become. And then after this, we have VY Canis Majoris, even larger. And then this last one is a theoretical star thought to only exist in the early universe and to have died out by now, known as the quasi-star, and its massive size completely dwarfs our solar system.
Right. And so some of these larger stars, at the beginning of the universe, when things were just kind of kicking off, some of these stars were growing to be massive. And so these are kind of where we might see some of these theoretical sizes. We don't really, to my knowledge, I don't think we see any stars this big currently. We haven't been able to observe any, but we think that they did once exist. And so now, after we look at kind of the different sizes of some of the stars out there, I want to briefly mention the HR diagram, which basically is a way to plot stars based on their luminosity, so their brightness, color, and their magnitude, their absolute brightness. The reason why I want to mention this is because I wanted to talk to you guys a little bit about kind of stellar evolution, how things are born, how they live their life, and then how they die. The sun is located kind of towards the center right of this plot on that little path moving from the top left to the bottom right of your screen. And this is what we call the main sequence. So when you plot stars in this way, if you take any population of stars and plot them like this, you find these different patterns, and these different patterns can be used to predict where that star is in its lifetime and see what's going to happen. So our sun right now is on the main sequence, as I said, and what that means is that in the interior of the star, nuclear fusion is currently going on, and it's fusing hydrogen into helium. And what I mean by that is basically you have this core of the star, and the pressure is so intense and the heat is so high that hydrogen can actually be fused together with other hydrogen atoms, and a new element is formed, helium. And now in stars like our own sun, they will be fusing elements maybe up to about carbon. And so as the sun will get older, it will kind of move on that main sequence a little bit, and then it will begin to kind of drift off into that giant phase that you're seeing on the right-hand side, and it'll become a red giant star, such as like Aldebaran, as you can see there, located in Taurus. So let's go ahead.
Before we move on, Jeremy, I do want to make a quick note that the HR diagram stands for Hertzsprung-Russell diagram.
Yeah, exactly. Right. And so the amount of nuclear fusion, I guess, that could go on inside of a star is largely reliant on the amount of mass that we have in that star. Let's go ahead and bring up the stellar life cycle chart, Parker.
Yes, sir.
And we'll give them an idea. If we can maybe blow that up a little bit. So here's kind of a couple different life paths that a star can be on. So our star, like the sun, like I said, is kind of an average middle of the road star. It's not very massive compared to some of the other stars out there. It will go through its life, burning its hydrogen into helium. And then once all the hydrogen runs out in the core, that core will begin to be creating some helium. But as that happens, the core will begin to contract a little bit, and the outer layers will begin to puff out. And I think we have a demo of what the fate of the sun is. Here's a nice end image. This is the Ring Nebula. And we'll get back to that in a short minute.
1 second here as I load up the data.
Yeah, so when we're loading that up, basically what that Ring Nebula is kind of the end product of what something like our star might do. So it's going to start puffing out those outer layers of different elements. And as that happens, the core will begin to contract, and it will become a white dwarf at its very center with these different kind of rings, or rather spheres of elements that it is shedding out. And so this end kind of phase or end product of stars, excuse me, is called a planetary nebula, which has nothing to do with planets whatsoever, but it's nonetheless the name that astronomers have landed on. Yeah, so here we see as that sun gets older and older, it begins to puff out those outer regions. It will puff out so far to completely engulf the orbits of Mercury, Venus, Earth, and then it will slowly fade out, and that Ring Nebula will spread out. And so this creates kind of, it starts spreading some of those elements that it was creating at its core throughout the universe. There is a much more efficient way of creating new elements and spreading elements throughout the universe, and that is in much more massive stars. So if we bring up that diagram again, Parker, and let's take a star like Rigel, a really massive blue star. When that star gets old and it moves through, it's going to be fusing elements in its core like hydrogen, helium, carbon, nitrogen, all the way up to some maybe elements all the way up to iron. Now, once it hits iron, iron is so stable in its core that it can't actually fuse into anything else. So when that happens, basically the pressure that is created from that energy can no longer withstand the gravity of that star. The star buckles in on itself and explodes in a very violent explosion called a supernova. And supernova are actually the supernova are the thing that actually creates all of all the heavier elements in our universe past iron. So things like gold, platinum, silver, all those things are created in these massive supernova explosions. And here we have a movie made, I think if this is in Monoceros, I believe, of a kind of like you could see that bubble kind of expanding over time, being blown out by that central star. Okay, it looks like we're at about 11:31. Let's go ahead and finish up with some star birth. So the universe is the ultimate recycler. Just because a star dies doesn't mean that the timeline ends. The universe kind of works in circles in this way, at least in the stellar life cycle. So supernovas, create all these new elements and scatter them throughout the galaxy, the nearby space. And over time, we get these giant gas clouds, molecular clouds, such as the Orion Nebula. So we could, I don't know if we have time to fly to the Orion Nebula, but can we maybe bring up some pictures of some stellar nurseries? And so in that picture that we started the show with, that Orion Nebula, we see these different filaments of all these different kind of elements, still mainly hydrogen and helium. Most of the space is actually hydrogen and helium, but we have these heavier elements. And so if you can think that like maybe, here's another really good one. So if you can kind of look through these images and you can find like little pockets of maybe little bright lights, that's where over time, all this gas and dust and debris is kind of being drawn together by gravity again, to the point where the temperature and pressure is so high that nuclear fusion starts again. Hydrogen begins fusing into helium once again, and a new star is formed. Here again is a nice, this is the image of the Eagle Nebula, which I guess if you turn your head to the left, you can kind of see like that eagle flying towards the top of the screen.
A good nickname for this to go along with it, these are also known as the pillars of creation.
Yeah, exactly. And very aptly named right there. Mm-hmm. And so in these stellar nurseries, in these nebula, this is, like where new star systems like the solar system are formed. All this gas and dust, contracts, as I said. And then do we have images of some different system formation?
Yeah, the thing going on at the bottom is a formation simulation.
Right, yeah. So some of those little dots were like new stars turning on. Do we have the ALMA disks?
Yes, 1 second. ALMA disks. And here we are.
Great, yeah. So this is a couple different telescope images of these early star formation, star systems being formed. There we go. And so in the center of each, you see that like bright new young star being formed, swirling all that gas and debris around it. And then all those little dark circles are areas where new planets are being formed. So if you have us go from a stellar nursery into this ALMA, these types of disks, wait about 4.5 billion years, then you get something like our own sun and our own solar system. So that was, let's see, we're at 35. That was a whirlwind, I feel like, of the stellar life cycle, but I want to make sure that we get to everybody's questions. So let's go ahead and start popping into the chat. Parker, can you go ahead and maybe turn off the slow mode, or at least reduce it a little bit so we can get some of those questions more quickly answered? Looks like Jillian or Gillian would like to know, will our sun ever be a supergiant, or at least bigger than it is now? Yeah, so as I was talking about, the sun will not be a supergiant, it will become a red giant. And basically that's as it goes through its life, it will begin to puff out those outer layers and become a red giant star, which will then slowly kind of fade out and maybe create something like the Ring Nebula. Let's see what else we have.
I'm actually going to turn this slow back on, but make it to about 5 seconds.
Yeah, it looks like people are wondering how long it is estimated until the sun dies. So the sun's been around for about 4.5 billion years. It's got about maybe 5 to 6 billion years left to go. So we're about right in the center of its life cycle.
Really cool.
Has anyone ever tried to walk on the sun? No, I don't think so, because it doesn't really seem like a great idea. There's not really any way that you would survive that. Let's see here. Yeah, Gingeroni points out that it's also physically impossible, right? So it's just like ball of gas and of ionized gas. So there's not actually like a hard surface.
And most people would be vaporized before they get to the surface.
Right, exactly. Yeah, so the closest thing is the Parker Solar Probe, like I mentioned. We have the orbit of the Parker Solar Probe, Parker.
The orbit?
Yeah, can we show them how close it's getting to the sun?
Yeah.
Let's see here.
So,
how close would you get before you felt the heat? Aaron would like to know. Well, I mean, we can feel the heat of the sun here, right? So even if you went to the next, closest planet from our perspective, even if you hopped over to Venus, it would be quite hotter. It would be a lot more hot. Yeah, it would be a lot hotter even at Venus, and then jump to Mercury, it gets even that much more hot, not much hotter.
Do we have an orbit button for Parker Solar Probe?
I know there is one buried in the system somewhere, but that's okay. That's okay if we can't find it.
Yeah, right now all I have is a picture of the probe.
Yeah, there we go. So here we see the image, at least, of the Parker Solar Probe studying the sun up close and personal. Just for reference, I think the closest approach of that Parker Solar Probe is about 18.7 million kilometers. It's about 7 times closer than any other spacecraft has been.
There we go. So there's the orbit kind of at the bottom there. I'm going to see if I can get up real quick.
Oh yeah, there you can see it a little bit. Those purple rings are showing how close it's getting. That innermost green ring, I believe, is the orbit of Mercury around the sun. Let's see. Any other questions about stellar death, stellar birth, where the sun is in its life cycle? I mentioned really, really big stars or really massive stars, can create these supernova explosions. If you have a star that's massive enough, even more massive than those stars, you can get something called neutron stars or black holes. Unfortunately, we're not going to have enough time to talk about those things today, but you can come back in 2 weeks. We have a whole show devoted just to black holes. So I know we'll be diving deep into those in that show. Let's see. Any other questions? Parker, do we have any other, maybe we could just show them some other images of supernova or stellar nurseries, or.
Here's the Omega Nebula.
Omega Nebula?
throw up the Dumbbell Nebula as well.
Right, and so what you're seeing in these nebula, the different colors, kind of many of these, I believe, correct me if I'm wrong, Parker, a lot of these are probably different, or like kind of false colored images. So a lot of these different colors represent different elements that allow us to see some of the different structure in these nebula.
Yep. I know that it depends on what wavelength you're looking in will determine how you see, like what colors you see these, and also whatever color mapping they put on their imagery.
Exactly.
Looking at an image, it's really good to look at the like details or like whatever it is like, wrote about the picture, because you'll learn quite a bit on what wavelength they're taking the picture in, what telescope might have taken it, and like what the color mapping might be for it.
Right, exactly. And yeah, just real quick to answer that question, Zion, what is their real color? So a lot of these stars are, emitting in non-visual wavelengths. So a lot of like UV light, a lot of have, kind of maybe putting out some of like X-ray light and things like that. So some of the actual colors might be kind of like a little bit reddish. I think the natural color of hydrogen when it's excited is usually kind of like a pinkish. A lot of oxygens, I think, if they're excited or ionized, I think usually turn kind of like a reddish color. So I think that might be a wrap. We're looking like we're getting close to our time, and I don't want to keep you guys too long. Thanks again, everybody, for joining us today. We really appreciate it, and we love to be able to, talk to you guys about this cool space stuff, even when we're not able to do it in our own planetarium. From all of us here at Fiske, thanks to you. Thanks to Parker for controlling the system and flying through all these awesome things with us. Thanks to Rami and Amanda for helping out with these questions and keeping the chat going. Make sure you like, share, and subscribe this video if you liked it. Tell your friends, help us grow. Next week, same time, same channel, we'll be doing a show about galaxies in the universe. So if you're more interested in, where these stars are forming, what these larger scales, above the scope of stars are, be sure to come check us out. Until then, stay safe, wash your hands, stay healthy, and keep your eyes looking up at those skies, guys. We'll see you guys next week.